Hi everyone, welcome to today's webinar, Ceph for Enterprise. I'm Phil Williams, Product Manager for Ceph at Canonical, and today I will talk about some of the challenges faced in the enterprise when it comes to storage and how we can use Ceph to solve them. Later I will be joined by one of our principal engineers, James Page, to give a demonstration of Ceph in action. Before we dive into talking about Ceph, let's take a few moments to revisit some of the storage challenges faced by IT departments in the enterprise. How the storage world has changed. We've come a long way since computers were programmed by paper punch cards, to the days where single hard drives were transported by forklift, and now to a time where you can carry a terabyte of data in a package smaller than a postage stamp. But what does this mean for the modern data center? Quite simply, organizations are storing more and more data every day. More and more business and administrative processes are completed online than ever before. Training data sets are growing larger and larger, and content creation is accelerating. It's becoming more apparent that for modern businesses, data is a new class of asset, and all of it needs to be stored somewhere securely and safely. As after all, what is a business without the data that forms its lifeblood? This growth and complexity are by far the greatest challenges for any storage or IT administrator today. Globally, we've seen near exponential growth in storage consumption, which is compounded by budgets that are not growing on that same curve, both in terms of hardware and the operators to look after those systems. Enterprise storage solutions are notoriously difficult to administer with clunky GUIs or CLIs that are difficult to script and automate around. And application behavior is changing too. No longer are apps just using block devices or file shares. Now there are applications who solely interact with object APIs like S3 and Swift. In many cases, data is stored across multiple systems, on-prem, off-prem, public cloud, and that makes management of that data even more difficult. As has been the case for what feels like forever, IT budgets are not keeping up with these growth demands, so we have to turn to innovative technologies to ensure that we are deploying systems that remain efficient. And whilst the public cloud can be a great answer for immediate needs or for proving out ideas, there are variable costs to be aware of. Typically, not only do you pay to store your data, but then you also have to pay again to retrieve it. As an example, over the years, I personally have worked with several companies who have had to pay tens of thousands of dollars just to migrate the data out of S3 onto their own dedicated private object stores when they've grown big enough to warrant building their own infrastructure. So all of these challenges, data growth, data importance, data management, silos of data, and budget lead us to some questions. How can we build scalable solutions that can grow without disruption, that are reliable, and are flexible enough to accommodate multiple use cases? And as data becomes more and more important to businesses, how can we match the cost of storing that data with its value? And finally, how can we prepare for inevitable disasters? Well, we can continue to look at the traditional storage vendors with scale-up solutions and potentially deploying different solutions for different access methods. Or we can consider a flexible open source alternative. So this is where we start to look at Ceph, and specifically Canonical's Ceph. Ceph is a massively scalable storage solution that provides multiple access methods to data stored within the cluster. Ceph clusters are built entirely from commodity hardware. Simply put, x86 or ARM, some SSDs and hard drives, and Ethernet to hook it all together. This leads to a relatively low cost or cost-effective solution when compared with traditional enterprise offerings. In Ceph, block needs are accommodated by the Rados block device protocol or iSCSI via a gateway, file needs by CephFS or NFS, and for object, we have the Rados gateway component, which provides compatibility for both the S3 and Swift object APIs. So, what does a Ceph cluster actually look like? At first, it can seem a little complicated with all of the various components. But let's break that down and discuss the purpose of them. So first, let's start with the mandatory components. Without these, the cluster won't function, so multiple of them are deployed for redundancy. So over here we have the mons and the managers, and then down here we have OSD nodes which contain OSDs. So these are all minimal components that you would need for a Ceph cluster. So the mons, or the monitors, they maintain a small 3-node or larger cluster, which maintains a map of the overall cluster state and its health. These maps get updated when, say, a disk or a node fails, which then triggers resync events to maintain enough copies of data. The mons are also responsible for client authentication, so whether you're accessing by block, you communicate with the mon first, and then that allows you to communicate with the data stored within the cluster. Managers, or MGRs, they're responsible for tracking performance metrics of the cluster and also exposing them to the Ceph dashboard and or external monitoring systems. It's a Prometheus endpoint that you can scrape, so you can drag all of that data into whatever dashboarding system you would prefer. Here at the bottom, we have a series of OSD nodes. I've arranged these into 3 stacks, and this represents our typical availability zones for a 3 replica configuration. So replicas of data will be stored across all of these availability zones, so it's important to separate them out into different cabinets, power zones, when deployed physically. If you were to use erasure coding, it's a best practice to match the number of availability zones to the number of shards within the erasure coding profile. So for example, if you used erasure coding profile 4+2, you would need 6 availability zones. Within each of these OSD nodes, there are a number of SSDs or flash devices and a number of larger capacity hard drives. At least in this example, you could have a cluster that's all SSD, all NVMe, or something that's a hybrid with persistent memory or Intel Optane sitting in front of sort of a mid-speed SSD or flash device as well. So there's lots of different options there. So the full form of an OSD is an object storage daemon. So I like to think of that as like a slice of CPU, a slice of memory, a little bit of an SSD because of the way that we handle caching, and then also the underlying hard drive. So these slices of the server, they all operate independently. An OSD on one node doesn't really understand what an OSD on the same node is doing. They work completely independently of each other. So with these mandatory components, that's a bunch of OSDs, the mons, the managers. You have a cluster that is capable of exposing block devices to RBD clients. So what about the other access methods? So we start having to add some additional components in here. So if we want to expose the object APIs, so S3 or Swift, we add components called the Rados gateway. For iSCSI block access, we add physical iSCSI gateway nodes due to the way that iSCSI is exposed by the kernel. And then for file, we deploy 2 or more metadata servers to handle all the metadata required for CephFS and for NFS. There is one additional group, the Liberados clients. So you could actually import libraries into say, your application that you're building that allow you to interact directly with the Ceph cluster and not having to use any of these like layered components too. So one of the challenges I talked about at the beginning of the session was that this data is typically spread across multiple storage systems and accessed in different ways. So the great thing with Ceph is that, as you just saw, we can start to consolidate all those use cases into one single storage system and that helps to reduce the management overhead of this particular type of storage system. For example, imagine the scenario where you're building a modern private cloud. That could be the OpenStack or Kubernetes based. But you have some older legacy workloads that are on aging equipment that you don't want to rebuild those applications and make them cloud native. You have a planned migration to use some other application in the future for the same purpose. But they were never really designed to work in a cloud native environment, so they have no inbuilt application resiliency, and they're always very much reliant on infrastructure resiliency. So, an underlying clustered file system on top of a clustered storage system, those kinds of, what feel archaic type applications now. So you could leave them on the storage infrastructure that they currently reside on, and potentially extend the maintenance for those storage systems, which can get kind of expensive. Or you could make use of one of the gateway solutions into the Ceph cluster. So if you have a block, an application that requires block storage, you could potentially expose iSCSI LUNs to it and migrate data there, and then that way the application still sees a block device. It doesn't have to use a new protocol. It can make use of iSCSI like potentially it always has done. Or you could use NFS if you've been using NFS before. CephFS could also be added. Behaves very similarly to NFS2. And that would then allow you to shut down that older legacy system, not extend the maintenance contract on it as well. Additionally, Ceph supports data at rest encryption and replication, but we'll talk about those features in a bit more detail later. Ceph's flexibility is key to answering the different needs of customer workloads and meeting cost and efficiency goals. Different data sets have different levels of importance and may require higher performing replicated pools within the cluster. These could be based on NVMe, and some data might just be an archive. It's seldom accessed, so can be stored on an erasure coded pool made from dense capacity focused hard drives. We may even access it that infrequently that it can be compressed to further save space and be more efficient. All block devices presented from a Ceph cluster are thin by default, allowing for a level of capacity over subscription. However, users should always carefully monitor the capacity utilization of the overall cluster to ensure that any hardware upgrades are always ahead of any demand. We don't want to get into a situation where we run out of capacity within any kind of storage system. And whilst you can build a high-performance NVMe-based Ceph cluster, what we should really do is try and understand the actual application use case. Sometimes it can actually be more beneficial to use local ephemeral storage with modern cloud-native applications. So, if you have an application that deals with its own resiliency and its own redundancy, it might not actually make sense to have multiple units of that creating their own copies of the same data set and then having a replicated data set sat in an external storage system. It may make more sense to allow the application to behave in this more cloud native fashion. One thing that's a little unique about Ceph is that our research has shown that instead of creating dedicated write-ahead log and DB devices for each object storage daemon, we actually see better performance by creating a Bcache caching device that sits in front of the entire OSD device. So then we don't have to deal with things like metadata spillover when the database gets to a certain capacity and things like that. And then this way, it also means that all of the reads and all of the writes to a device can be cached on flash. Whereas if you're using a segregated WAL-DB device, it's just the writes and the metadata that get cached. Ceph also has some features to help with disaster recovery scenarios. So most commonly used are local snapshots of RBD devices. So that's just a block snapshot. Or object versioning within Router's gateway buckets. Both of these features can help protect against simple mistakes like deletion of files, or which provides you kind of an easy rollback opportunity. And as shown here, to protect against more catastrophic situations, we can replicate RBD devices and Rados gateway buckets to secondary clusters in physically diverse locations to protect against larger scale failures. Like the loss of power to an entire data center, for example. This kind of configuration is easily supported using Juju relations, but in a cross-model context, where the underlying applications, so in this case Ceph, they're running under different Juju controllers using different MAS deployments in different locations. Just for clarity, MAS is Metal as a Service, so that's how we deploy physical hardware within data centers. The only thing to point out with any kind of local and remote replication is that, of course, if the storage system can do it, that's great. But then we also have to be conscious of how the rest of the infrastructure and applications would react. You can't just pull a block device from an application and replace it with a previous snapshot and expect things to continue operating normally. There's some application integration that does need to happen. And the same thing when you fail over between diverse sites. How an application reacts to that really depends on the application and the design work that's been done for that kind of deployment. The world over, data security has become a super hot topic. One of the ways that Ceph can help with meeting some of those compliance objectives is the encryption at rest feature. So firstly, Ceph supports Ceph's native block-based device encryption, where the keys are managed by the Ceph monitor cluster. So that's the 3 monitors I talked about. But secondly, we can also support the use of Vault for key management. So this is facilitated by a tool called Vault Locker. It's super simple. Vault Locker will generate a key, encrypt the OSD block device, and store the key within Vault. Then on reboot of a storage node, it will retrieve the key and unlock the block device ready for use by the Ceph cluster. So why Vault? Well, Vault has a number of features, including encryption of all data and multi-key unseal, which make it really quite secure. So in a deployment where Vault is simply deployed in LXD containers alongside Ceph, this means that if servers or indeed entire racks of servers are stolen, then it's impossible to retrieve the encryption keys without the required number of unsealed keys used to unlock the master encryption key. So this is like it's almost like multi-layered or multi-factor unlock, if you will. And of course, this also means that returning failed disks to the manufacturer becomes risk-free, thus reducing costs where it was previously impossible to know if any data could maybe be recovered from that disk. And you would typically destroy those disks and then just have to buy brand new replacements and get no credit from the manufacturer for the failed device. Deploying a Ceph cluster requires a lot of planning, from the physical arrangement of hardware in the data center to power distribution, network planning, and that's before you should even think about the individual servers and their specifications. This complexity is why we offer cluster consulting and deployment services, where our field engineering or professional services teams work collaboratively with customers to define and deploy the most suitable cluster configuration for a specific use case or multiple use cases. Whilst Ceph, and Juju remove a lot of the complexity of operating a Ceph cluster, some customers actually prefer to treat their storage as an on-demand resource and rely on Canonical's managed services to operate Ceph clusters within their data centers, but on their behalf. They want to think of a storage system a little bit like a public cloud offering, and don't want to worry about the day-to-day operation of the cluster itself. So what are the benefits of Ceph? This is a little bit of a recap. The underlying architecture of Ceph allows a user to start with a relatively small cluster and over time add additional nodes to grow in line with their needs. Obviously, this is not as easy as with the public cloud, where everything is on demand, but with careful planning, expansion can be staggered to keep a little bit ahead of growth demands. Ceph is very reliable. In fact, the cluster's number one goal is to ensure that data is always protected. And in the early days of working with Ceph, this behavior would catch people out. For example, when adding or removing nodes, you could trigger large resyncs, which could, in the early days of Ceph, would cause performance issues. Thankfully, this is well understood now, and we can safely carry out those changes with little to no impact at all. Ceph is highly flexible. We can create a single cluster that serves multiple needs. For example, we have some data that we must keep, but we don't access it very often. So alongside general purpose storage pools, we could create another pool that's more aligned to an archival use case with very dense drives and maybe even reduce the amount of cache that we give to those drives too. As I mentioned several times already, from a single cluster we can serve block, file and object needs. We can automatically upgrade the Ceph cluster between releases of Ceph without interruption. Security is very important when it comes to data, and with Ceph we can deploy OSDs with at-rest encryption so that when a drive does fail and it has to be returned for warranty purposes, there's no risk of exposing sensitive information. And finally, Ceph can provide a very cost-effective storage solution, primarily from reduced capex by utilizing off-the-shelf hardware. Instead of having to buy something proprietary and only supplied by a single vendor, you can take off-the-shelf components to build a cluster. And from an operational point of view, its self-monitoring and self-management also reduce cost there too. You don't have to jump on failures immediately. The cluster will work around those failures and then you can deal with them in regular maintenance windows. So now we have an understanding of the challenges of storage admins and a basic understanding of Ceph and Ceph and how it all plugs together. Where can we actually apply it? So Ceph can provide storage to all these different infrastructure products. So OpenStack, Kubernetes, VMware, XD, and even to normal Ubuntu server workloads. Ceph is by far the most popular storage backend for OpenStack. It's used in over 70% of OpenStack deployments, based on the latest stats from the Open Infra Foundation. It has very tight integration with the different components of OpenStack, so Nova, Cinder, Glance, and Manila, and as well as integrating with Keystone for authentication. There's also a CSI for Kubernetes that allows Kubernetes to use a Ceph cluster for persistent volumes, both RBD, so block, and CephFS for file system-based storage. And then block storage needs from VMware can also be accommodated via the iSCSI gateway, and of course LXD can use RBD for container images. As more and more modern cloud-native applications are deployed, there is less interaction with the physical infrastructure. Applications themselves interact directly with the storage system's object APIs. They don't think about file systems on block devices or NFS shares and the files and the folders within those shares. Take, for example, a web application that's used to upload videos and then distribute them to a CDN. That could actually make use of the Ceph Rados gateway and the S3 API. The application uploads to the API. Once the upload is complete, that can then trigger distribution to a CDN. So that would then pull the object out of the Ceph object store as the CDN origin, and then push it out to the remote caches. Many modern backup solutions can also directly stream to object storage. removing the need for complex tape libraries and cumbersome tape rotations and offsiting processes. So if you have a Ceph cluster that's offsite, you could just point your backup solution directly to the S3 API within presented by the Ceph cluster, and avoid having to do something more complicated with tapes and rotation and stuff like that to provide offsite backups. Additionally, Ceph can support file share use cases with CephFS and NFS from the same cluster, as well as those block and object workloads that we've already talked about. And now it's demo time, so over to James Page. He's one of our principal engineers, and he will give us a walkthrough of a Charm Ceph deployment.
Thanks, Phil. I'm going to take a low-level look at a Charm Ceph deployment being used to support two different clouds. The first cloud is an OpenStack cloud, which is using the Ceph deployment in a variety of different ways through the various storage features that Ceph provides. The second cloud is a VMware ESX hypervisor, which is leveraging the iSCSI gateway capabilities of the Ceph deployment to access storage provided by Rados block devices. Let's start by taking a look at the Ceph deployment itself. We're going to skip the Juju GUI and drop straight to the command line for this demo. For the purpose of this demonstration, we've deployed a small Charm Ceph cluster consisting of 3 physical storage servers, with the rest of the Ceph services mainly deployed in LXD containers on top of the same infrastructure. The exception to this is the Ceph iSCSI service. This part of the solution makes use of a number of kernel capabilities and as such must currently be deployed directly on hardware, in this case alongside 2 of the servers hosting OSD devices. This is commonly referred to as a hyperconverged architecture, and this deployment also hosts OpenStack services in the same way on the same infrastructure. As you can see, the deployment is using the latest Ubuntu LTS release, 2004, which includes the Pacific release of Ceph alongside OpenStack Xena. Let's log into the Ceph monitor cluster and check out a few details. The deployment already has a number of pools configured for the various use cases we're going to be looking at. These make use of the Ceph PG Auto-Tune feature, which ensures that the placement configuration for each pool is optimized based on its actual storage usage. We can see the same services displayed in the Juju status output represented in the Ceph services: Mons, managers, MDF services for CephFS, OSDs, Rados Gateway, and TCMU runners, which are the iSCSI gateways. We can see that each of the servers is hosting 4 OSD devices, all of which are registered as SSD class. In fact, each of the OSDs is a 7K spindle fronted by an NVMe cache tier using Bcache. Bcache provides a performant caching solution in the Linux kernel for reads and writes across different underlying block device use cases, allowing more cost-effective, larger capacity spinning disks to be used in conjunction with much faster SSD and NVMe-based solid-state devices. Let's move up the stack and look at our first consumer of this Ceph deployment, OpenStack. I've deployed Charmed OpenStack alongside Charm Ceph and pre-created some images and some instances and some volumes that those instances are booted from for the purposes of this demonstration. Let's switch back to the command line and take a look at the low-level details of how this all hangs together. OpenStack consumes Ceph storage services in a variety of ways, all making use of the Ceph native interfaces for each use case. Rados block devices are used in a few different ways. Images stored in OpenStack for use by cloud users are stored as Rados block devices, which means they can be used to create instances on the cloud. Images are stored in the glance pool in RAW format. This allows copy and write snapshots to be used when creating new instances using these images. As the instance root disks are children of the parent glance image, only the delta between the image and the instance is stored, up to the full size of the volume created for the instance, which is 30 gigabytes in this example. The second use of Ceph storage as part of an OpenStack cloud that we're going to look at is object storage. OpenStack provides an object storage service in the form of Swift. However, Ceph also provides a Swift and S3 compatible service which can be integrated with OpenStack for authentication in the form of the Ceph Rados Gateway. To demonstrate a typical use case of object storage, I've uploaded some HTML-based documentation to this deployment. Okay, let's move on and take a look at the second cloud that we have deployed and using the storage services being provided by Ceph. VMware ESX does not have native support for Ceph, but does have good support for enterprise storage protocols such as iSCSI. With Ubuntu 20.04 LTS and Ceph, Ceph can be exposed using the iSCSI protocol using the Ceph iSCSI gateway. The iSCSI gateway makes use of the Linux kernel's LIO capabilities to provide iSCSI targets for use in platforms such as VMware ESX, or indeed anything else that can communicate using iSCSI. The Ceph iSCSI charm provides operational actions to easily create iSCSI volumes and set up security of iSCSI initiators. I've already completed these operations for this deployment and have configured the iSCSI block devices as a VMFS data store in ESX. Let's have a look at what this all looks like through the Ceph dashboard. As you can see, the iSCSI gateways are operating in a cluster. State is replicated via Ceph between the servers, configured as part of the deployment, ensuring consistent configuration across all targets. Disks are fully multipath via each target, with each target owning any specific disk at a given point in time. If the target suffers an outage, another member of the cluster will take ownership of the device, with switchover supported by multipathing and the client accessing the block device. I've configured a volume for use by the VMware ESX hypervisor. Let's take a quick look at the ESX server consuming this iSCSI device. This is the iSCSI disk presented by the Ceph iSCSI gateway to ESX, and here is the VMFS data store that I've created on it. In a VMware vSphere deployment, this configuration would be managed using vCenter rather than on each individual hypervisor. iSCSI devices can be used by multiple ESX hypervisors, and VMFS is a cluster-aware file system supporting storage for virtual machines across a vSphere deployment. The last feature of this deployment that I would like to show you today is the Ceph dashboard. Charms to support deployment of the Ceph dashboard were included in the last release of Charm Ceph and integrate the dashboard with other Charm services such as Grafana and Prometheus, which are used to provide reporting of performance metrics from across the Ceph deployment. Using the dashboard, we can easily check on the overall health of the deployment, as well as drilling into detail about specific aspects of the deployment, such as the object storage daemons running. We can even drill in and look at performance data from across the object storage daemons. This information is provided using Grafana and Prometheus. Okay, that was a bit of a whirlwind tour of some of the capabilities of Ceph to provide storage services to Ceph-enabled platforms such as Ubuntu OpenStack in a highly integrated way, as well as providing storage using established enterprise protocols such as iSCSI to a VMware deployment. And we've also provided an overview of the Ceph dashboard, which can be used to monitor and configure your deployment. And now I'll hand you back to Phil.
Thank you, James. That demo was great. Finally, there is one question remaining. With all the different ways of deploying Ceph, Ceph ADM, Puppet, Ceph Ansible, why use Charm Ceph? Canonical keeps a close track with the upstream releases of Ceph, but also maintains long-term support versions, long after the community discontinues support for certain releases. As seen in the demonstration, the nature of Juju and Charms allows for a model-driven application approach to deploying Ceph, which allows easy visualization between the various components and independent scaling of those different components too. MAS integration allows for automated hardware deployment with availability zone information passed automatically through to the Ceph deployment. Not all Ceph vendors are able to offer kernel live patching or are willing to support encryption at rest, with some resorting to hardware-based solutions, and that kind of undoes some of the commodity approach of Ceph. Online upgrades with ChamCeph are really quite straightforward, just by changing the cloud archive source, upgrading the Cephmon charm, and then the other Ceph components you can easily upgrade to the next release. Importantly, Canonical not only provides a reference architecture document that can be used as a blueprint to build a private cloud, we actually use that very same architecture for our internal clouds too. An overview of ChamCeph can be found at ubuntu.com/ceph. In fact, this is really the only page you need to visit, as all of the others are linked from there. You can try out Juju and ChamCeph by following our docs and find out more about our managed services and consulting offerings on their respective pages too. Please use the Contact Us form or live chat on the landing page to get in touch. I'd just like to say thank you all for joining the webinar today. I hope the information presented and the demonstration was useful. This is where we can switch to the Q&A portion of the webinar. I can see a few questions in the chat, so let's get started answering those. Alrighty, now that I can finally unmute. So the first question we have in the live chat is, what about hyperconverged infrastructure? So that's the whole point of today's webinar was really just to talk about Ceph as being a segregated storage solution, so not something tied to an OpenStack deployment or a Kubernetes deployment. It's absolutely possible with ChamCeph to deploy in a hyperconverged configuration. In fact, that's what we use internally for one of our production clouds. We have a number of drives within each hypervisor that are dedicated to Ceph, a bunch of SSDs, well, actually NVMEs, that are dedicated for the Bcache volumes, and then a bunch of drives that are used for local ephemeral storage and boot and those kind of things. So it's absolutely possible to deploy in that way. Next question we have is, where can I find more demos? So in terms of demos, I think the best thing to do is actually go to ubuntu.com/ceph/install and try it yourself. It's a really quite easy small deployment that you can sort of play around with on your own machine. So that's probably the best way to get started with it. And then, did you discuss licensing options? So we don't actually license ChamCeph. ChamCeph is available freely. It's completely open source. What we do offer is a support service around that, and that's called Ubuntu Advantage. So we have two support offerings there. One is business hours only type support, and then we also have 24/7 365 coverage as well. Let's clear these ones out of the way. And this one might be one for you, James, if you don't mind. Is CephFS copy on write? I believe so, if you have the snapshots in place.
Yeah, I believe if you're using snapshots, there are some copy on write features within CephFS. But you know, I guess there's option to do that at the end of the day. But.
And do you know about the extended attributes? That's definitely something I'm not sure of.
I have to admit, I'm not aware of the extended attribute support in CephFS, so it may be there, but we need to go and check.
Yeah, what we can do with that one is I'll after the webinar finishes, I'll get a list of all the questions, and I can always follow up on that one. Do you have any document or best practice for hyperconverged infrastructure? Yep. It's another thing. If you get in contact with us, we can start sharing that information with people. We've worked with a bunch of different hardware vendors to produce, bills of materials based on specific hardware that's available from those different vendors. So any support for SMB, James?
At this point in time, there is not support in ChamCeph. However, the Samba packages in Ubuntu are enabled to support a CephFS-based backend through the VFS layer in Samba, but that's not something that we have automatically deployable as part of a charm Ceph deployment today.
Gotcha. It is something we're kind of interested in. It doesn't come up. We don't see lots of people asking for it. It's something that we've sort of kept on our backlog, concentrated on a bunch of other things. So maybe in the future we'll add it. Just it really depends on demand.
For the 2204 release early next year, we should have NFS support using Ganesha.
Mm-hmm. So during the talk, you mentioned using 3 replicas for the backend pools. Can I use 2 replicas to save space?
You can, but it's not advised. Obviously, with every replica you drop, you lose some level of resilience in terms of the number of drive failures or host failures that you can tolerate. And when we deploy Ceph as part of charm Ceph, we are really talking about host failure rather than the drive failure. That's the failure domain that we default to, unless availability zones are available within the deployment, in which case we'll automatically use those to give you zone level resilience rather than host based resilience. So yeah, you can use 2 replicas, but it's not recommended. It means if you have 2, if you lose 2 hosts that happen to be hosting 2 parts of a PG for a replica set, then you're going to be back to that single replica, which will then have to service both active I/O and recovery operations at the same time. So,
and I guess if you only have the 2 replicas, and in that period of time where you've not rebuilt the PGs, you're going to only have 1 replica. So you're going to end up in read-only mode on that replica as well. So that could impact writes.
As long as the pool is configured at size 2, it should be fine.
Okay.
It will work, but again, like I said, it's not recommended. So.
Yeah. Here's another. Any support for deduplication? So at the moment, no, there's no deduplication option. I guess you could call it an interim option is for pools that are either like an archive type pool. You could enable compression to get a little bit of extra space saving there, but it really depends on just how much you want to eke out of the Ceph cluster. This might be one for you, James. Can you please elaborate on the replication mechanism of OSD nodes? Should I imagine something like DRBD?
Actually, it's quite significantly different from DRDB. DRDB very much is a point-to-point block replication to provide kind of like a mirroring capability for a block device between 2 or more hosts. There's some different features in there depending on how you have it configured. With an OSD, the pool that's hosting the Rados block devices has a number of placement groups configured for the data that's stored within it, and each placement group then has placement information about where the replicas that constitute that placement group are stored across the cluster. So the OSDs all talk to the monitors and to each other for availability monitoring, and they figure out whether the required number of replicas have been met and how those replicas need to be distributed across the hosts. So a block device, if you've got a 40 or a 50 machine cluster, if it's a big block device, it could be spread across all 50 machines, depending on which part of the block device you're accessing and where the replicas that support that chunk of the block device are actually stored. So it's a true horizontally scalable block device rather than just a mirrored point block device.
Thanks, James. So one more question: how can we contact you? So I think the best thing to do there is if you go to ubuntu.com/Ceph, there's a green get in touch button there. If you contact us in that way, that's probably the easiest way to do things. Otherwise, reach out to me directly. My Canonical email is philip.williams@canonical.com, and I can either answer questions or get you in contact with the right people internally. So another question around DR. So Ceph cluster to another Ceph cluster in another location. Is that async?
It is asynchronous. So for both the Rados gateway and for Rados block devices being configured to perform replication to a remote cluster, they're both asynchronous replication options. So the primary cluster is not waiting on a return of confirmation of a write to a secondary cluster before it returns to the client.
Absolutely. And let's just take one last one, I think. So with Charm Ceph, James, how long does it take to deploy a Ceph cluster?
It was relatively quick. To be honest, a lot of the time taken during deployment is actually how long it takes the server to post, which is improving, but is still relatively slow, and it has to do that twice during the deployment, once for machine provisioning and then post reboot, and then the Ceph is actually provisioned on top of that using Juja and Charms. However, that said, it's still not particularly slow. We're talking small cluster, probably be deployed within 15, 20 minutes tops. And then as you have more and more machines, obviously that takes a bit longer. A lot of them are done in parallel. So it won't be incrementally larger depending on the number of machines that you're adding. But it's pretty quick.
Great. And it looks like we're actually out of questions. So I guess we'll wrap up there. So thank you, everybody, for joining today. And James, thank you very much for putting the demo together and for joining me for the Q&A. And as I mentioned already, ubuntu.com/Ceph, and you can get in contact with us that way. And yeah, great. Thank you, everybody.